So I was perusing some more step 2 step questions when I found in the 2016 paper this question number 7. And anyone who's a loyal fan of the channel will immediately see why this caught my interest. Number one, because it's integration, and of course I'm down to do integration pretty much no matter what, down for whatever, as long as it's for integration. But also because if you look at this integral right here, I made a video like last week, I think, on how to integrate stuff like this. So really interesting that we're now going to do similar sorts of things based on another idea. Really, really cool stuff. So anyway, it's asking us first to show this thing. This is not hard to do. We're going to make the substitution x equals, oh, sorry, going to make the substitution something like x equals a minus u, just to get from something that looks like this to something like this looks like this. Okay, so that's fine. It's obviously dx equals minus du, so we're just going to have to put a minus there, and we get this when x is a, u is 0, and when x is 0, u is a, so we end up making this whole thing there. And yeah, this minus can be used to swap the two limits of integration over. And now, we've started here, we've got to here, we've got u's instead of x's. But as in a previous video that I made a couple of days ago, we can now use the fundamental Taylor-Swift law of integration, which is, or we can write this whole thing out twice for no reason. But the Taylor-Swift fundamental theorem of integration is that you can use these dummy variables x, and you can change them to whatever you want. In this case, of course, Taylor-Swift. And that only works for definite intervals, because of course, like when you do the integration, no matter what the integration makes, you're just going to put those numbers into the letters wherever they are. So the letters just go away; they're rendered irrelevant. So this u's, these both u's here, they can just be written as x's. A is just a constant, so it doesn't matter, and the limits don't change. And we end up with this equals this, and the first part of that is all done and dusted. So yeah, I made a video talking about how to do this the other week. But now it says to use star, so we're going to use star. So okay, let's take this integral and say from here, a is pi over 2. We can just write this as f of pi over 2 minus x. So every time we see an x, we're just going to replace it with pi over 2 minus x. And apparently this integral is the same as this one based on the proof that we just used. So okay, we've got some compound angles to do here. So sine is the one that goes sine cos minus sine cos, if there's a minus here. So it looks like this. Sine pi over 2 is 1, and cos pi over 2 is 0. So this just makes cos of x. And I'm not going to write it down, but do the same thing for the cos one, which goes cos cos plus sine sine, if there's a minus here. And of course, the cos still goes away, so it just ends up being plus sine of x, because sine of pi over 2 is still 1. So that just ends up being a sine. These become coses, and you end up with this here. This is kind of interesting. So you've now changed this integral into a very similar one, but with a cos. So what I'm going to do is I'm going to write the whole thing out once again for no reason, just a fan of doing that today. Let's call this integral I, and this one here j. And now what I'll notice is that I and j are equal to each other, of course, because I've got a line that goes from I all the way to j. So I and j are equal. But also, if you add I and j together, what happens? Well, you just get the integral of 1, because you get sine over cos plus sine plus cos over cos plus sine, which is just 1, right? And so you integrate 1 for x, and then you put in pi over 2 minus 0, and you get pi over 2. So, of course, if these two things are equal and they add to make pi over 2, that means each one of them must be pi over 4. Kind of cool. Anyway, question number 2 does not say use star to evaluate. So what I'm going to do, just in the interest of being different, is I'm going to do this in the way that we did it last week, which is set up an integral a bit like this. And if you're wondering where this comes from, of course, you should just watch all of my previous videos ever, and that way then you'll know, because you'll have seen the one that has this in it. But what I'm doing here is I'm setting up a linear combination on the top of the function that's on the bottom and then its derivative. And you'll see why that works. But what we'll do is we'll say this whole top row here has to now equal sine to make, of course, these two integrals the same, which means, of course, that a minus b is 1 and a plus b, looking at the causes, is 0. This very simply gives us a as a half, b as minus a half, which we can now put in here. And the reason this works beautifully is because now we can split this fraction in half down the middle there. And these two things cancel. The integral of a half is just a half x. And these two things don't cancel. But if you've got f dashed of x over f of x, that's just a log of f of x. So we end up with a half x minus a half log of that function there. We can put in our limits. And of course, when you put in 0, you get 0 minus log 1, which is just 0. And when we put in pi over 4, we get we get root 2 over 2, I guess, plus root 2 over 2 is just root 2. So that's where that comes from. And we end up with that whole answer there. Root 2 is 2 to the half, so then you bring the half out and you can write it a bit more simply like this here. So that's part 2 done. It didn't explicitly tell me to use star, so I think I got away with that. Part 3 also doesn't tell me to use star, but unfortunately I haven't made a video very recently on how to do this in a different way. So I am just going to use star and hope that it works out. So okay, replace the x's with a minus x's, a being pi over 4 again. We can use the tan double angle formula. Now tan of a minus b goes tan of a plus tan of b. No, it doesn't. It's minus first, isn't it? Hang on. Tan of a plus b is the plus, then the minus. So minus must be the plus, must be the other round. It must be this here. Yeah, this is a minus in the usual one, so that becomes a plus, and that one is the minus. Yeah, perfect. So this is all good. I think that's in the formula book, is it? I don't know, I guess. Tan pi over 4 is 1, so this breaks down into this. This is really cool now, because what you can say is, obviously 1 is 1 plus tan x over 1 plus tan x, so combine these. The tans on the top cancel, you just end up with a 2 over 1 plus tan x. You can write this using log laws as log of 2 minus log of that thing there. And then you can split this this integral into two integrals. And what you notice, of course, is that this second integral is just the thing you started with. So you have I equals this thing minus I, which means 2I equals this thing, which means I is half of this thing here. Of course, you can just literally, yeah, that's what I've said. Yeah, this just integrates to x log 2, put in the pi over 4 to get pi over 8 log 2. Oh, because I've divided by 2 already, so you get pi over 8 log 2. Yeah, perfect. And that's all she wrote. Perfect. Third part of this is also done. Part 4 then, and finally, again, don't have any better ideas that I can do this, so I'll just follow the rule, which I'm supposed to have been doing the entire time. This one ends up being annoying, and it's actually why I didn't bother for this one, and I used my thing instead, because pi over 4, when you use the compound angle formulas, just doesn't, it's just not as nice, right? Because you end up with all of these 1 over root 2's at the front. But actually, it works out okay, aside from that. Cos is, by the way, if you have a minus, you get a plus, and with the sine, if you have a minus, you're going to get a minus, I think. So, okay, the cos one is going to turn out to be this. I'm going to factorize out the 1 over root 2 in front of it, so it ends up being a bit like this. And then this one is the same, obviously, so it's just cos plus sine, and I've factorized that 1 over root 2. I'm also going to get a 1 over root 2 from this one. Clearly, it looks a bit different, but basically the same. It's going to be 1 over root 2, and then it ends up being cos x minus sine x. Again, you can do that on your own, but this one turns into this with the 1 over root 2 factorized out, this one into this, and this one into this. Of course, this time this is a half, but then the signs cancel in here, and you get 2 cos, and so they cancel with the half, and you just end up with a cos of x on bottom like this. So this is what you get. Really cool. We can now split this integral in half down the middle here to get this. And the reason that's great is because following the logic, we now have this integral equals this one minus this one, but that integral is the same thing as what we started with. So we can add it to both sides. We get 2 lots of the original integral, is this thing here. I've factorized out the pi over 4 because it obviously doesn't matter to the integral to get this here. And of course, if I divide that by 2, all I have to do to answer this remaining step question is try and figure out how to do this integral here. And, you know, you look really closely through all the stuff you've done before, but you can't find anything helpful, so that doesn't really work. This is just a really beautiful piece of work. It's just so sneaky. I've left a space for myself, dx, over there. And the reason I've done this, and by the way, there's probably lots of other ways you can do this, but this is just a beautiful way of doing it. Times top and bottom by sec squared. Because then you obviously end up with sec squared on top. And on bottom, of course, sec squared is 1 over cos squared. So the first term just becomes a 1. And cos x times sine x times 1 over cos squared x is just sine x over cos x, which is tan x. And can you see where I'm going with this? It's just absolutely stunning. Because, of course, now the bottom of this fraction here derives immediately to the top. So this just integrates to log of 1 plus tan x, which is just gorgeous. And so, of course, now we're pretty much done here, right? We're pretty much done. We're just going to throw in the pi over 4 and the 0. When you put in 0, you're going to get log of 1, which is 0. When you put in pi over 4, tan of pi over 4 is 1. 1 plus 1 is 2. And we end up with this answer here. Just a great question. Really enjoyed doing it. So yeah, thank you for watching.